All right, let's go over these. I'm not sure if you had enough time or maybe we're not positive on the approach here, but this is just a quick review of limits. The nice thing is we're going to teach you another way to do this today, and that's the whole reason why we're doing this problem. The very first part is, remember, x squared minus 4 can actually be factored into x plus 2, x minus 2. And when that happens, the x minus 2's reduce out, and I'm left with a brand new limit of the limit as x goes to 2 of x plus 2. Now I can do substitution, and I end up with 4 as my answer. Do notice, I should have probably mentioned this earlier, but if I plugged in 2 right away, so if I plugged in 2 right away, I end up with 4 minus 4 up top, which is 0. And then if I do the same thing on the bottom, I get 2 minus 2, which is 0. And I end up with a 0 over 0. This is actually something we're really interested in today. It's called the indeterminate form. But that doesn't give us an answer. And as we saw, because of algebra, the limit as x goes to 2 of this function is actually equal to 4. So if a limit can exist, but the original limit ends up being an indeterminate form, what other methods do we have for solving it? Because we're not always going to be able to factor, and that's the idea today. Now, this one here you might remember, and this is, I often find students forget about this one. And the only reason why I'm allowed to do what I'm about to do is because we go to positive or negative infinity. Remember, that's as I go to the really, really far right of the graph. Where is this function headed? Well, since infinity is such a strong, large number, the only parts that we go to the far, far right of the graph that's going to actually affect it are the leading coefficients and the degree of the numerator and the leading coefficient and degree of the denominator, which means this little x plus 2 isn't going to have any effect on the graph as I go to positive or negative infinity. And if you remember it, this is titled our end behavior model. All right, so we're dealing with the end behavior, which allows me to get rid of, I think I actually refer to it as fluff, any of that extra stuff. Because now what happens if I plug in infinity? Well, I can't plug in infinity right away, but this monomial over a monomial allows me to reduce out a value of x from top and bottom. So the actual limit is -3 over x to the third. I just got rid of an extra x value here. Now you could have done that earlier because each one of these has a factor of x, but what about now if I plug in infinity? Well, infinity to the third power is still infinity. And now what do I have? I have a number divided by infinity, which is actually 0. And we're going to talk about that in a second, why a number divided by infinity is equal to 0. But I just wanted to give you a quick overview of review of limits. The nice thing is you're going to also notice that today we have a different method. I should have pointed out, what if I plugged in infinity right away, right? And I have to be careful with my equal sign. Notice how I didn't say equals, I drew the arrows. We're going to be focusing on that today as well. But what if I plugged in infinity in here? Well, -3 times infinity would be negative infinity. And what if I plugged infinity into the bottom? That would add to infinity. When I have infinity over infinity, or negative infinity over infinity, the infinities do not reduce out because they're actually different infinities. The top number isn't approaching infinity as fast as the bottom number. And there's a lot more going on here, but this piece right here is another indeterminate form. We don't like when we have infinity over infinity or 0 over 0. And that's our goal today is how do we, when we get that initially, what else can we do to solve these kinds of problems? Really quick, I just want to make a mention. I think we've got one, two, three people who have not signed up for the AP class, for AP Classroom yet. And if you have not done that, today is the absolute last day until you get charged a $40 late fee. Now, if you already talked to me about not taking the course for next trimester, that's fine. Then you don't have to worry about signing up for AP Classroom. But if you are planning to continue on with calculus, you need to sign up for AP Calculus and the exam. And do remember, it is free to cancel the exam. But if you try to sign up tomorrow, then it's an extra $40. All right. The other thing is when you signed up, you did not pay for it yet. It's $50 per exam or $10 if you're on the free and reduced lunch program. Um, that will come out soon. We got a new system for payment, and it is in its like finalizing process. So we'll just let you know, and I'll make you aware of when you have to go on and just pay for that. But know that because you signed up in AP Classroom, you don't have to pay for the late fee anymore. Okay. Um, I don't want you to write this whole problem down. What I'd like you to do is just write the equation P of t. And I want to just make a special note. We're actually not going to spend one specific day on section 4.1 because we've been doing this all along. Section 4.1 is called application of the derivative, which basically means, hey, now that you've mastered, hopefully mastered, um, all of the derivative rules that we've learned, the product rule, quotient rule, chain rule, power rule, plus all those derivatives of the functions, can you now apply them to context problems? And that's what this is all about. So it's just an extension of what we've been doing. And my job or my goal is to just kind of over the next month is keep throwing random warm-up problems in that deal with context. So this is going to be the first one. You don't have to write this whole description, just write the equation. A population of bees migrated to a town in the Midwest. Suppose the population of bees in the town at time t, which is in weeks, can be modeled by the function p of t. So here is the model for our population. All right. What I'd like you to do then is see if you can answer the first two questions. Find the initial number of bees that were in the town, and then figure out how many bees are in the town after 1 week. And the intent is you're going to be using your calculator on this. Okay, so I want to show you basically a couple of tricks for making problems like this a little faster. And we'll see if my graphing calculator simulator works to show you even more tricks here. And that's the goal with this problem today. So part A is find the initial number of bees in the town. Initial number is whenever t is equal to 0. So we're just plugging 0 in. Notice this isn't really even a calculus problem right now. I have, unfortunately, this might work. Let's see. There you go. Okay, so I'm hoping you guys can see this okay. But I want to show you one little trick with problems like this. So I'm going to have to do when t is equal to 0. And then for part B, I'm going to have to figure it out when t is equal to 1. So is there a better way to do this? If you have your graphing calculator right now, go ahead and hit y equals. And we want to type this function into the calculator. Now there's a little hint here that I think is really, really helpful, and it's dealing with fractions. I learned this a couple of years ago from my students. If I hit the green alpha button, alpha and then y equals, That gives me kind of a separate little menu. And the first option is just creating a fraction. So it automatically puts it in a fraction. Now, I'm not positive. I don't think this works on the TI-83 calculators. I think it might be only for the TI-84. But what I can do then is then I don't have to really worry about putting parentheses around the numerator and parentheses around the denominator. If you have a TI-83, then you got to put parentheses around each numerator and denominator. It's never a bad thing to do that anyways. But then I'm going to plug in the equation itself. And then instead of x, we're going to use, or instead of t, we have to use x in our equation. So all I did was type that into y equals. And then I need to figure out two possible answers. I got to figure out one when t is equal to 0, which you could do without a graphing calculator. And then the same thing when t is equal to 1. Well, the nice thing is if I just go to a table, so if I go second table, here's all the information I need right here. And if I want more of a decimal when y is 0, or x is 0, y is 30, that means there were 30 B's initially in the town. And then if I scroll down, it gives me the full decimal here instead of just a truncated three decimal number there. So I'm going to have to jump back here, but what do we know about P of 0? P of 0 is 30 B's. And then for P of 1, you don't have to show any work. This was 37 point, and we definitely want to take 3 decimal spots, so we could round it to the 3rd decimal spot, so 881. 37.881 B's at 1 week. Right, so after 1 week, it's 37.8 B's. Now, that's nothing special, right? You guys have known how to do that. The thing that we haven't talked about is right here. How do we deal with the rates of change in our calculator? Now, if you don't have a calculator, I definitely want you to pay attention. If you do have your calculator, hopefully you are step by step with us, and let me know if I need to review a couple more things here. Okay, so there's some important words in part C. Find the rate of change. Well, right there, that means slope, right? But another word for slope is derivative. Now, why do I know that this is derivative instead of just a regular slope problem? Because of the word exactly. So I want to find the slope or derivative, which is the derivative of p, so p of t, exactly at 1 point. Now, I have two options. I could do the quotient rule, and I could write out all my work, but if I'm allowed to use my calculator, we don't need that at all. And this is brand new, so I didn't show you this before, because I didn't want you to rely on it. But let me show you something. All right, so we have y equals into our equation. You know what? I just thought of this. I wonder if I can zoom in a little bit more so you guys can see it. That's about as far as I can go. I hope you guys can see this okay. Please let me know in the chat, or just mute yourself, Strub. We can't see it, or I'm lost. I don't know. Let me know what's going on. But let me show you what we do. We plug the equation into y equals, right? And then you can hit a graph. Now notice, at 0, we're going to be at 30 B's. And then it's an exponential function, so this is going to grow pretty quickly. So I don't think my window, my standard window, is going to be really nice. I could try to hit graph, but notice I need to see more kind of on the y values and maybe even more in the x values. But I'm going to increase the y pretty high here. So I'm going to increase the y's up to like 200. I'm thinking 200 b's total. Might take a while to get there. And there's a graph. That's not too bad. Now, what do I want to find? I want to find the derivative. Okay, so there's two options. Um, if you go second calc, now you've dealt with all the ones 1 through 5. You dealt with 1 through 5 in Algebra 1, Algebra 2, pre-calculus. Look at option 6, dy dx. That's the derivative. We've never done this before. So if you go to option 6, and again, how did I get there? Second trace or second calc, option 6. And then this is the weird part. It doesn't tell me what I need to do. So what I need to do is, because I want to find the rate of change at 1, I'm going to type in 1. So this is going to say, oh, you want the derivative at 1. Notice up here it says calc derivative at point. So calculate the derivative at 1, hit enter, and there it is.
Which button did you press to get there?
Second calc. So you got to hit the second button and then the calc button, and that'll be option 6. We're going to do it again here in a second. I just want to throw this over here. So what does it do? Remember, kind of just a quick, how does this work? Well, what it does is it takes the tangent line and it finds the slope at that tangent line, which is the same as dy dx. And that's what it is. The derivative at the points x, y is right here. So you have to learn how to read this as well. There is my derivative. So I'm going to write that a little bigger. We've got 8.804355, and you could round that to 3 decimals if you wanted. But what does that mean in the context of this problem? Right? We just found the rate of change of the bee population. So we have the bee population is, now notice this is a positive value. So if my derivative is positive, that means the bee population is increasing at a rate of 8.804. You could stop there if we rounded to 3 decimals, or you could give the whole thing. But then I have to include the units. Well, what does this mean? This is referring to bees per week. And then we have to add one extra piece to this, because it's not just bees per week. This is bees per week exactly at week 1. All right, so notice how I described this. I referred back to the problem. The bee population is increasing at a rate. I gave the rate. Now, if this was a negative, then I would keep the numbers, and instead of saying increasing, I would say decreasing. But I wouldn't say decreasing at a negative. All right, so we just say increasing at a positive, and then I gave the units, bees per week, but then I told them exactly where that was happening. All right, let's try it again, but this time let's figure out, what about when x is 20? Right? What's happening? How fast is this going at week 20? So I need to use my calculator and find the derivative at 20. All right, now we do have to change our window a little bit, so you got to be careful here. Notice if I'm going my x values, I need to be out here at least at 20, because right now it looks like I can't get past 10. So make sure you're kind of with me here step by step. This one I might see if I can, that actually doesn't do it justice. I think it's better this way. So first thing, I'm going to hit window, And then I need to see more in the x maximum. I need to see further to the right, and I got to go at least to 20. So I'm going to put 30. All right, and then hit graph. All right, now I have to find the derivative at 20. So I'm going to go second calc, go to option 6, and then you just have to know it's not really going to prompt you. You have to type in 20. And notice it doesn't, it's off. It's actually way off my screen, which is fine, but see dy dx right here? That tells me the answer. So even though I can't see, I should have probably changed my y maximum to something a lot higher, but I was still able to get this answer without having to see that on the window. But notice you have to read this then. So you actually have two pieces of information that are super interesting here. I'm going to answer the question, but then refer back to what do we know? So we know the derivative at 20, right? Because that's what I typed in, is 52.97417. And what is that referring to? That's referring to bees per week exactly at the 20th week. So exactly at week 20. And then you could also state that the bee population is increasing because it's a positive derivative. Okay, the last thing I just want to quick point out here is look at what else they gave you. They gave you the derivative, the slope. But wait a minute, they also gave me the point. Why would they give us that? Or another question, what else could I do with that? Well, given a point and a slope, very, very quickly, I have the equation of the tangent line. So you're probably thinking, Strud, you could have told us this 3 weeks ago and saved me a whole headache. Well, there's a reason why I didn't show you that yet. All right, so what do we have? We have a point, x, y, and we have the slope. Write the equation of the tangent line. All right, when you are allowed to use your calculator, you can do this, which means, notice, we really didn't have to show any calculus. We just had to understand what the technology was telling us. Okay, so that is just a let's use our calculator piece. We're actually not going to use the calculator for the rest of today. We're going to venture into another avenue here that is dealing with limits, and it has something called L'Hopitals Rule. So I will give you a second to write this down. Okay. So let's talk about L'Hopitals Rule here quick. L'Hopitals Rule just states whenever you see an outcome of 0 over 0 or infinity over infinity. Now notice this could be positive or negative. Um, these are called indeterminate forms. And what that means is we don't know if the numerator is going to go to 0 first or the denominator, which means we just cannot determine the solution right now. However, as we saw in the warm-up, there are other methods for evaluating the limits. So somebody named L'Hopital ended up finding a method that allowed us to solve if they existed limits that resulted in indeterminate forms. And the method is, instead of taking the limit of the original functions, we're going to take the limit of the derivative of the numerator and the denominator. So there's one thing that I think I really have to stress. When we're saying when we're doing a limit and we notice that it's an indeterminate form, that just means we cannot determine our answer yet. So you cannot say that the limit equals 0 over 0 or infinity over infinity. Never ever say that. You have to be very purposeful with what and how you use your equal signs in calculus. Right? And then the other thing to note is that all the derivatives that we've learned, they're all fair game. They could appear. So product, quotient, chains, powers, inverse trigs, everything is fair game, which is why we spent as long as we did learning those derivative rules. So what we're going to do is we're going to actually look at L'Hopital's rule with the two examples that we just did in the warm-up. So you actually know the answers to these two problems already. My goal is to get you guys to show proper notation. So some of you who know you kind of try to do shortcuts and you don't want to show all your work, you're going to be the ones that are in trouble for this specific concept. And the reason why is because if you skip a step or you don't justify this correctly, then you're not going to earn the full points. And I want you to model kind of exactly how I do it. And this is what I'm expecting for every problem. Okay, so the first thing we have to show is that the given limit results in an indeterminate form. But I can't put an equal sign right here. And this is, I have to like resist the urge of doing that. What I have to do is I have to show that the limit of the numerator goes to 0 or infinity, and the limit of the denominator goes to 0 and infinity, but I can't use the equal sign because it's not going to be an equivalent. It's not going to equal 0 over 0. So let's show you what we would do. So you have to rewrite the limit of just the numerator. All right, and this is the step that kids often skip. They think, why do I need to do that? Well, according to the theorem or this rule, they're saying if the limit of the numerator, and if you don't put the limit as x goes to 2 of the numerator, then you're not following the first part of this idea. So then we're going to just plug in 2 squared minus 4 is 0. So I just showed that the top limit went to 0. Now notice, I'm not putting a divide bar either. I'm just saying, now I have to show the bottom limit. And notice how I'm writing out the entire function again, right? I have to show that this limit goes to 0. Now you don't have to show the intermediate step here. You don't have to show this algebra if you can do it in your head. All right, and then notice how I didn't really use an equal sign except for this limit right here, but I didn't say that the given this original limit was equal to anything here. I'm just checking. Now what we're going to do is we're going to compare the top to the bottom. Notice I didn't put equals. Well, I always put a frowny face because this means that 0 over 0 is the indeterminate form, meaning I can't determine my answer from 0 over 0. So that work right there is the work that you need to show that is basically our ticket to using L'Hopital's rule. Because I resulted in an indeterminate form, now we're going to apply L'Hopital's rule. Now notice, the limit is still the same. But what I'm going to do now is I'm going to take the derivative of the top. All right, well, to start, we're going to have some pretty friendly derivatives just so you guys get the process and the idea down. Then we're going to build on harder or more challenging derivatives. So what do I have? I have x squared minus 4. Well, the derivative of x squared is 2x. The derivative of 4 is 0. And then on the bottom, I've got the derivative of x minus 2, which is just 1. Well, now, notice, if I plug in 2 here, I get 2 times 2 over 1. I can now put the equal sign because I know that this will result in an answer. So I'm just going to do direct substitution. I'm going to plug the 2 in for x, and I end up with 4 over 1, or 4. And that is the answer that we actually ended up getting in the wormhole. So we know that that is the correct answer, which basically gives us a little proof that L'Hopital's rule works. All right. So let's look at another one. It's up to you if you want to write this one. I'm going to go just a little bit faster because I want to get to ones that are more challenging. Now you hopefully can look at this and see if you put infinity here and infinity down here, you're going to get an indeterminate form. However, just because you can do it in your head doesn't mean that you're allowed to skip the most important step. I have to show the limit as x goes to infinity of just the numerator is equal to, in this case, negative infinity. All right, now notice I didn't use an equal sign. So yeah, great question here. What if the top and the bottom don't equal 0 over 0 or negative infinity over infinity? We'll talk about that. That's going to come up here in a second, but we'll talk about it. So then I have to do the bottom. And again, you don't have to show the intermediate step here. You could just say, well, this is going to be infinity. But I get infinity plus infinity, which is positive infinity. So now notice, I need to then compare. And you don't have to write the word compare, but by doing the limit of the numerator over the limit of the denominator, I end up with another indeterminate form. I get negative infinity over infinity. What it means is we don't know if they're approaching infinity at the same time, at the same rate, or if one is going faster than the other. So that is our ticket to do L'Hopital's rule. And all L'Hopital's rule is, after you state this first part, is taking the derivative of the top over the derivative of the bottom. So the derivative of the top is negative 3. The derivative of the bottom is 4x to the third plus 2. Now you can check here, because this is one of the questions that just popped up. What happens if I don't get infinity over negative infinity or 0 over 0? Well, watch what happens here. Now, I'm pretty confident that I can put equals here because the top part is going to stay negative 3. The bottom part, if I plug infinity to the third power, that's going to be infinity times 4 plus 2, which is just infinity. And then I end up with negative 3 over infinity. Now notice, that is not an indeterminate form, but it is something interesting. Every year I have kids that get confused by this, but if I take a number and I divide it into an infinite amount of pieces, those pieces are going to be so small that it's going to equal 0. So notice, that is actually an answer that I like. 0 is a good response to a problem. 0 over 0 is not. Infinity over infinity is not, but a number over infinity, we know that's going to be 0. Okay. So every year I have kids that have a hard time kind of visualizing this or understanding, well, wait a minute, why does that equal 0? So here's what I like to think of. Let's say that I got a rope that's 10 feet long. And if I have a rope that is 10 feet long and I divide that rope into an infinite amount of pieces, so I just cut it up. So 10 feet long, I cut it up to an infinite amount of pieces. How big is each piece? Well, it's so small that you can't even see it, that it's going to be 0. It's basically going to look like it doesn't exist. That's what I think of when I see a number over infinity. Okay? Well, what if I flip that around? What if I have a rope that is an infinite length and I divide it into 5 pieces? Well, cutting infinity into pieces still results in infinity because infinity is more of a concept than it is a number. Right? So that's just some things we're going to think about here, and that's on the next slide. I've got this kind of written out a little better. It's up to you if you want to write these things down, but we've got just some important things that come up with dealing with L'Hopital's rule that it's good to keep in mind. Okay, so let's think of a couple things here. What if I have a number divided by 0? Well, that's the 10 commandments of math, right? Thou shalt not divide by 0. So anytime you have 0 in the denominator and a number up top, we know that that is an undefined solution, right? It doesn't exist. You could say undefined or you could say does not exist. Both are acceptable. But what if I have 0 divided by a number? Well, 0 divided by any real number is 0. What if I have a number divided by infinity? This was if I had a rope that was 10 feet long and I divide it up into an infinite amount of pieces. That's equal to 0. Or what if I take infinity and I divide it by a number? You can't break infinity up because when you break infinity into pieces, it's still infinity. So these tend to kind of confuse kids. Just it's more of a number sense thing. You got to be aware of that. The other thing that we've talked about this before, but the other thing that kind of confuses students is this idea of e to the x. And my suggestion for this is to think of the graph, right? We basically just saw this graph in a slightly different form, but we saw an exponential graph with the bee population. So we have to think of a couple of things. What do we know about the graph y equals e to the x? Well, e to the 0 power, anything to the 0 power is always 1. Anything to the first power is always itself. So e to the first power, we're just going to call e. What about e to the infinity power? E to the infinity power, well, if I go to the far, far right, if I go out to positive infinity, my graph is going to be way, way up, which is infinity. So those ones students are pretty good at. It's the next one right here that I want to just show you how we can think of this now. That is helpful. If I have e to the negative infinity, well, the negative exponent is just going to bring that down in the denominator. So I get 1 over e to infinity. But wait a minute, don't we know that 1 over e to the infinity, isn't that infinity? We just saw that right up here. So now 1 over infinity, well, what is that? Well, let's check here. 1 divided by infinity is equal to 0. And our graph supports that as well. As I go to the far, far left here, as I go to negative infinity, this function is getting closer and closer to 0. All right, and then we've got the natural logs. And it's been my experience that students often forget this graph. And I think if you can remember what the graph looks like, you will, and this is a very poor sketch, which is fine. It should be more curved. I just wanted to try to make it go through the right point. So we get y equals ln of x, right? Well, let's think of this. What is the natural log at x equals 0? Well, at x equals 0, there's an asymptote. There's a vertical asymptote, which means this is undefined or it does not exist. Right? And then what about when x is equal to 1? Well, that's right where this crosses. So that's equal to 0. Now you could really, let me show you why this is true. You don't write this part because I'm going to erase it. But what if I raise both sides to the power of e? Right? If I raise both sides to the power of e, what happens is I get this idea right here. This is kind of like a change of base formula. E and ln go away, and you're left with 1 equals e to the 0. That's why the natural log of 1 is equal to 0. All right, and then what happens as I go to the far, far right on this graph? So as I approach positive infinity from the right, this graph is going to keep on going up. And then what about e to the negative infinity? What is that equal to? Well, this does not exist because if I look over here, as I go to the far, far left, the graph isn't even possible. So that does not exist. All right, so those are just important things to keep in mind. I think visually, and that's what helps me kind of memorize these pieces, but there's also, you could do change of bases and get these as well. Okay. We are going to jump into a couple other pieces here. I'll have you write the first one, but not the second one. So we're going to do L'Hopital's rule. Well, actually, our job is just to evaluate the limit. Let's determine whether or not we have to use L'Hopital's rule, because it's not always the case. We have the limit as x goes to 0 of sine of 2x over x. Now you might remember this. There's a trick. If you think graphically, you already know this answer is 2. Right? So L'Hopital's rule isn't always the best way to do it, but L'Hopital's rule will work if a limit exists. And it has to be a quotient too, by the way. You can't do L'Hopital's rule if it's just a function. It has to be a quotient, a function divided by a function. All right, so what are we going to do? We're not going to put the equal sign. We're going to say, I need to just check the limit of the numerator. Right? And almost every time, it's just a substitution, but you have to show this part right here. Now, I can put an equal sign here because we're not saying that this is equal to this. We're saying that we're just checking the limit of the numerator. So I'm going to do sine of 2 times 0, which is just the sine of 0. Well, then I have to think, and hopefully this is something that is just burned in your brain right now. When I go over 0, that's the spot 1 comma 0. I know what cosine is, and I know what sine is. So I know that the sine of 0 is 0. And then this is, I know that you can, I know you know the answer to the bottom right away, but you have to show this work. Okay? You have to write the limit as x goes to 0 of the bottom. And then if I just plug in 0, I get the bottom. And you don't have to write the word compare, but you do have to state that when you do compare it, you get 0 over 0, which you don't have to write that's an indeterminate form. I put a frowny face, just that's kind of my way of saying, okay, this does not result in an answer. So that's my ticket to do L'Hopital's rule. So in L'Hopital's rule, we're still going to the same limit as x goes to 0. But now we're just going to take the derivative of the top. Notice there's a chain rule. I will say anytime you're doing L'Hopital's rule, you should think there's going to be a chain rule, right? So the derivative of the outside is cosine. Keep the inside, and then multiply by the derivative of the inside, and the derivative of the inner 2x is just 2. Right? And you could clean that up, but you're going to see we don't really need to. And then the derivative of the bottom is just 1. Well, anytime you get something reducing out top and bottom, you're most likely going to get an answer in your next step. Because if this is 1, then I can just plug 0 in right here very quickly. So I might even skip the 2 times 0 and just write that's going to be 0 times 2 over 1. And then you just have to know what is cosine of 0. Well, cosine of 0, we already basically set it up. Cosine of 0 is 1. So that gives me 1 times 2 over 1. And there we go. Now we know the answer because of L'Hopital's rule. Now I will say there are going to be times where L'Hopital's rule doesn't work on the first time. You have to take the derivative again and again and again and keep going. And sometimes it doesn't work at all. And in that case, the limit just would not exist. Okay, I don't want you to write this one. I want to do this very quick just so you guys can see it. So let's take a look. If I do the limit of the numerator, that's just going to be the natural log of infinity, which we knew went to infinity, right? And then if I do, notice I didn't put equal signs. I'm taking the limit of the denominator, which if I just plug in infinity, I get infinity over infinity. I compared them. Indeterminate form, which means now I have to apply L'Hopital's rule. So I'm going to take the derivative of the top over the derivative of the bottom. Now I'm going to do this first. If I take the derivative of the bottom, that's just 1. If I take the derivative of the top, the derivative of ln of x is 1 over x. But look at, I have a fraction over a fraction. We don't really like that. So let's think of it this way. The 1 is going to stay in the numerator. The divide by x is going to go down here. Well, notice now I can actually plug in infinity times 1, which is 1 over infinity, which results in 0, right? 1 divided by infinity is really 0. So that was just a quick little thing. If you have a fraction, fraction in the numerator, you can write the numerator up top and the denominator of that in the denominator of the original. All right, this is the one I want to get to. This is most likely the types of problems you're going to be seeing for sure tonight. And it's just a little bit more going on. But the nice thing is the process is still the same. So you don't have to write all these words, evaluate, write your answer in simplest forms. But go ahead and just write the limit. And then we're going to do the limit of the top and the limit of the bottom separately. And notice I didn't use equal signs. But we do have to write that out first. You have to tell the reader that you are taking the limit of just the numerator. Okay? And don't forget the word LIM as x goes to 0. That's, if you miss that, then this is gibberish. It doesn't make sense. Well, now we can actually do substitution. And technically, negative 0 is still just 0. So this is really e to the 0, which is 1. So I get 1 minus 1, or 0. On the bottom, we got to take the limit of 3 sine negative x plus 3x. Now we're just going to do substitution then. And then I'm just going to solve each piece. We know that negative 0 is still 0. And I know that the sine of 0, we saw that on the other example, the sine of 0 is 0. And 3 times 0 plus 0, that whole piece is 0. So if I compare the top limit to the bottom limit, that is the evidence I need. I have to show that to show the indeterminate form. If you don't write 0 over 0, they're not going to give you one of the points that this problem would be worth. But that's our ticket to do L'Hopitals Rule. And you can see, even before I start writing, I'm thinking, oh, I'm going to have to take the derivative of the top. Notice there's a chain rule here because of the negative. And then inside here, there's also a chain rule as well. So don't ever forget the chain rule. And now we're just going to take the derivative. Derivative of e to the x, if this was just an x, it's e to whatever was on the inside times by the derivative of the inside here. Well, the derivative of negative x is negative 1. And maybe for your notes purposes, I'm going to write chain rule here. And then I am checking the derivative of the minus 1 is 0. I don't have to put the plus 0 here because the derivative of a constant is always 0. So there's the derivative of the top. Then we've got 3 times sine of negative x. I got to find the derivative of this piece. Well, the derivative of sine, the 3 is just a multiplier, so it's going to stay. But the derivative of sine is cosine. We're going to keep the inside, but then I have to multiply by the derivative of the inside. And the derivative of negative x is negative 1. So there's my chain rule again. But then I also have the plus 3x. I have to take the derivative of the plus 3x, which is just 3. So you can see why we studied all these derivatives. We need those facts, and we need to be really good with the chain rule to continue on with doing all this stuff. So now I'm not sure, and this is the part where I don't want to get in trouble, so I'm not going to put an equal sign. I don't really know if this is going to result in a 0 over 0 or infinity over infinity. You might be able to figure it out. I'm going to do just to be safe is I'm just going to show the work again, because if this results in a indeterminate form, then I would have to do the same work I did again up here. So I'm just going to do the new numerator as x goes to 0. All right, well, you'll notice e to the negative 0 this is really just 1, right? 0 isn't positive or negative. So that's 1 times negative 1 equals negative 1. And that's a good sign that I'm not going to get an indeterminate form because I have a number instead of a 0 or infinity. But I'm still going to check the bottom then. And you could simplify this. I just decided not to. You could put the negative 1 out here. But now I'm just going to plug 0 in here. I think now I'm going to take this negative and put it with the 3. So it'll be negative 3 cosine of negative 0. So I don't write that negative because I put it on the outside, plus 3. And then we know that negative 0 is really just 0. Cosine of 0 is 1. So I end up with negative 3 plus 3. Yeah. Which gives me 0. Now, what happens when I compare these two? I get negative 1 over 0, which is not indeterminate. I just can't divide by 0, so that tells me that it doesn't matter. My overall limit just does not exist. All right? Really, if you get the process of L'Hopital's rule, the only difficult thing is just once you get the indeterminate form, taking the derivative and then checking it again. Now notice, I could have written this one as without putting these limits because this went to a number and that went to a number, but I just can't divide by 0, so it doesn't exist. All right. I just want to show you this last one. Don't write it down. We're going to go fairly quick, but it just has an interesting result. So I think it's just kind of important for you guys to see what's going to happen. So right away, I'm going to take the limit of the top. So we know that the limit as x goes to infinity of ln of x is really the natural log of infinity, which is infinity. And then on the bottom, I have the limit of 2 times the square root of x as x goes to infinity. Well, the square root of infinity is still infinity, and 2 times infinity is infinity, so when I compare those, I get the indeterminate form, right? So that's the work that just gives me the ticket to use L'Hopital's rule. So now, watch what happens here. Okay? When I take the derivative of the top, we saw this again, the derivative of ln of x is 1 over x, but that's a fraction. If I have a fraction in the numerator, I can just make it a 1 over x as is. And then I have to take the derivative of this part. Now, I might do some side work here, and I might just say, okay, if I want to find the derivative of the bottom, remember first, we don't like the square root. I'll do it that way. So we're going to rewrite the square root as the 1/2 power. And now the derivative is just a power rule. The 2 and the 1/2 come down, and then I take one away up top. So if I subtract 2 over 2, I get negative 1/2. The 1/2 and 2 go away. So I end up with x to the negative 1/2 in the denominator. Now I could rewrite this as 1 over the square root of x as well, which is fine. I could multiply this as 1 over square root of x, but actually it's going to be better just to write it like this. So it's better to take this piece. Now, here's why. This is x to the first power, which I could write 2 over 2. So I'm going to use the equal sign because I'm just doing algebra right now. All right, so the top is going to stay 1, but down here, this is the same as adding the exponents, or because it's negative subtracting. So really, when I do this, 2 minus 1 just tells me I have x to the 1/2. So a little bit of algebra simplification allowed me to rewrite this. And now, what if I plug infinity in? I have infinity to the 1/2 power, which is the same as the square root of infinity. But square rooting infinity is still infinity. And I end up with 1 over infinity, or 0. So you just kind of have to be aware of some algebra tricks to make things work out for you. And that happens every so often. Okay, so here's what we got. We're going to do this one on Monday or Tuesday. Your homework tonight is 6 problems. I'm going to ask that you show all of your work, the correct steps for L Hopitals Rule, and then you're going to submit your work. Instead of doing a screenshot of the Delta Math 4.4 Day 1 L Hopitals, I don't want to see the screenshot. I want you to submit your work to Schoology. Last thing is the Chapter 3 test. So you are able to view the Chapter 3 test now. So you can open that test up. You can see which problems you got right or wrong. If you want to correct any problem that you did not get 100% on, show your work on a separate sheet of paper, be neat, accurate, and then email me a photo. And if you do that, I will boost that score up to a 75%. Okay, so I'll be available from 1 to 2 in my office hours. If you need more help with the test corrections, or if you need help on L Hopitals Rule or anything else, stop in and see me. We have about 7 days left of the trimester and we're done. So good luck. That's all I got. I'm going to create a breakout room and talk to a couple of you here quick. So look for that.